Shall we start? Okay. Okay. Thank you, everybody. Thanks for joining our meeting today. So today we have Dr. Hamid Shirkhani and as a presenter. Dr. Hamid Reza Shirkhani is a research officer within the Sustainable and Resilient Infrastructure and Communities Group in the Construction Research Center of the National Research Council Canada. His expertise and research interests involve resilient and sustainable infrastructure, climate change impact studies, numerical modeling, and water resource engineering. Dr. Shirkhani serves as a CSA Technical Committee member for the development of new and updating existing Canadian standards. He is also an adjunct professor of civil engineering at University of Ottawa, Carleton University, and Queen's University, and is an associate editor for the journal Frontiers in Water. I really welcome Dr. Shirkhani, and we are very glad that having him for today's presentation. Dr. Shirkhani, uh, yeah, we are
Thank you very
waiting
much for the
listen for
yeah.
you.
Thank you very much, Hamid, for the presentation, for the nice introduction. It's my pleasure to be here today and get to know everyone and this nice community of engineering and the society of and the society that you've actually established and developed through the years. It's really a pleasure to be here, and thanks for the invitation. So today I'll be talking about the impact of climate change a little bit. Actually, the focus of my talk is about the climate change implications for design and maintenance of infrastructure. And I'll try to address some challenges that we deal with currently due to climate change and how our infrastructure systems will be impacted by those changes. And as I mentioned, I'm gonna go over some challenges because, as you may know, there is currently a gap between the climate science and engineering practice and engineering practitioners that needs to be addressed. And in my research, in one line of my research, I try to bridge the gap with more advanced models these days, and with the advancement of climate models and the more sharing of data and access to data. Engineers really need to understand the impact of climate change first, and then they really need to know how to use those data that will be available to them more and more every day. So today I'll try to touch on those concepts a little bit, and then I'll show some design parameters under climate change and how they may impact the way that we design our infrastructure, and most of all, how they can actually impact the existing and aging infrastructure across the nation. So first, let's start with climate change. So we know climate is changing, that's a fact, and the science is clear about that. 97% of climate experts believe that humans are responsible for the global warming. Actually, as it was mentioned in the video, like human activities resulted in higher and elevated concentrations in the atmosphere, and the elevated greenhouse gases resulted in global warming, higher capacity for holding energy and heat. And then those warming and raised level of warming resulted in a change in the entire Earth climate. And the impacts are already being felt, in particular by Canadians. So I can show you some examples here. Thawing permafrost, increases in heat waves, and wildfires and floodings are among some events or catastrophic events, I would say, that Canadians experienced within past decades. So, and then it's good to have a look at our infrastructure systems in the nation. So first, I'll start with the southern infrastructure. As you know, most of the population in Canada They're living in the southern part, and these infrastructure they provide a great economic and social benefits to the people, and they are major assets for us, for people, and also for government, for different levels of government, for municipalities, and so on and so forth. And as a matter of fact, they serve large population of people, and our day-to-day life and the quality of our lives depend on the quality of the infrastructure. You can think of different examples: roads, pavements, buildings, bridges, water network, sewer systems, and so on and so forth. And as I mentioned, our everyday life depends on the quality of those infrastructure. So at the same time, in particular in Canada, we have northern infrastructure. As you know, most of our infrastructure in the northern part of the country, they are built on permafrost, and they rely on a stable permafrost. However, the permafrost is dying under climate change. And when you go to northern communities, you will find some kind of seasonal infrastructure, such as ice roads that you might be familiar with. Um, and then those ice roads are critical for those communities because usually they provide food resources, water resources, and so on and so forth for the communities in the north. And then under climate change, the stability and the actually the length of having access to those types of infrastructures are shortening. So here I'm showing an interesting figure from NASA Earth Observatory. So as you can see, there is no simulation, there is no model. We are looking at observation. We are looking at the comparison between 1984 to 2012, and it's clear that the ice is gone. The Arctic ice is shrinking, and that's a clear indicator of global warming. So in Canada, coastal infrastructures are of essential importance. So they provide a lot of economic and environmental benefits to the society and to the communities. And for example, we can think of sea level rise under climate change that can be exacerbated by global warming, and that can be a real threat to many coastal infrastructure in Canada. Another example that will have some implications also for hurricanes and for environment in particular, and for the ecosystem, is the rising water temperature in our coastal areas. And last but not least, indigenous peoples, we need to think about the small communities that we have, in particular in the north. As you know, most of our small communities in the north, they have access to substandard infrastructure systems, and that makes them more prone to the impact of climate change. That being said, that the global warming levels will be much larger at the north of the country in future, as I'm going to show some examples later on. So, and then the impact of climate change will impact our infrastructure. So these are some examples from West. You can think of wildfires in prairies, longer summers and drought, and heat waves in Ontario, Quebec that we experienced previously, and flooding, and then different types of infrastructure failure due to, for example, wash of the road and so on and so forth. In our coastal areas, we have storm surges due to the level of the raised level of water and the impact of the storm, and so on and so forth. And then, as I mentioned, in the north, we can think of the loss of permafrost or permafrost thawing that can result in catastrophic events, and so on. So it's clear from historical observation that Canada has been warming actually, and then it's expected to continue to warm under future climate. And on average, Canada is warming twice the global warming rates, and that's attributed to different factors. I'm not going to go through the details of that. And then on top of that, the northern part of Canada is even warming at higher rates compared to the global warming. And then that can result, as I mentioned, and that can actually increase the frequency and the magnitude of the extreme and catastrophic events across the nation. So although the focus of today's presentation is not on mitigation, uh, I'm going to show just a little slide here about the mitigation. Canada has a target for the year 2030, and I think the video that was shown was very timely because that was in one of the video. There was an African guy talking about the cause of the climate change, and he said we are not even contributed to the changing climate, and now we're paying for that. So that's an international effort, and Canada is trying to play its role here. And there is a plan to reduce the emissions across the nation. And there are several initiatives and several policies in place in order to get to that target. For example, you can think of carbon pricing, moving toward a more green generation of electricity. And then you can think of built environment. They're moving toward more sustainable ways of built environment and building our infrastructure. For example, we can use solar panels to generate electricity sometimes that we need in our homes. Electric cars, they are good examples in transportation sector. They can contribute to the reduction of emission of GHG gases. And then in the industry, for example, in the mining or in the tailing dam industry, there are many ways that with the improvement of the technology, we can reduce the emission of the GHG gases. And then it goes all the way down to all the sectors related to engineering, forestry, agriculture, and waste management, for example. And then here we're looking at the historical and projected future GHG emissions of Canada. The black line is showing the historical measured values. And then there are three different projections. The red one is based on the 2015 data. And then the blue one is showing the 2019 version. And then there is another one, which is the green one, and that's showing the 2019 projection based on the additional measures to be followed for reduction of the emission of the gases. And you can see here the target. You're trying to get here at year 2030, but even with implementing additional measures, we are still far from that. And it shows that we really need to improve in that area. But as I mentioned, that's a global effort, and then one country cannot make it. Yeah. So yeah, let's get back to the focus of the presentation, which is on adaptation more and the impact of climate change and what are the implications for design and the maintenance and rehabilitation of our infrastructure. So knowing the impact, we can say that we need to build the resilience in our infrastructure, and then we need to invest to strengthen the resilience of our infrastructure. And it is not possible except by using codes, standards, and guidelines which are based on future climatic data. And in this way, we can reduce the climate-related hazards and disaster risk at the first place. And then that some examples here is, for example, we can protect ourselves against the floods to increase the flood resilience. And then there are some adaptation plans for indigenous people, as I mentioned earlier. So I talked a little bit earlier about the northern communities. I have a good example here that things are different at those part of the country. So for example, we are looking at the bridge here. It looks to us, maybe it looks like a very small bridge connecting to a part of the road, and then there is a small river. But this bridge failed at some point, and then that disconnected two major parts of the city, and that created a lot of problem for the people in that community because they couldn't get access to the food and water and some other resources which were located at the other end of the bridge, actually. So yeah, we really need to pay more attention to the northern part and the small communities and to provide some solutions that work for them. So a flood, as you know, is the most costliest natural hazard for Canada. And one idea is to bring the flood resilience to an acceptable level across the nation. So in these two figures, I'm showing two examples of two different types of flood and flood consequences. In the first one at the left, we see a storm surge in a highway in BC. I took it from the recent Canada's climate change report, which was published in 2019. That's a very good piece of document, and I really encourage you to go over it if you have time. And it also provides a summary, so we can go over it to see some interesting topics about the climate change in Canada. The second figure is also showing the consequence of flooding, which is kind of an erosion here. And you can see that the road is totally damaged due to that events. So again, we need to develop some codes and standards and guidelines, but we need to base them on future climatic data instead of using historical ones. But that is a challenging task, and I'm going to show some of those challenges today. So thinking of the climate system, we can identify different components here, different different subsystems, I would say, that they work with each other in the climate system. So, for example, we have the ocean, we have land, we have atmosphere, and then within each of these systems, we have some other processes and some other systems. For example, you can think of cloud processes, and on land, we have some water processes, and so on and so forth. And then these components, they are interacting with each other. For example, we have the sea ice interaction, and ice is melting, contributing to the sea, and then there is evaporation, which is contributing to the cloud processes, and then precipitation, and so on and so forth. So if I want to describe the climate system, I use this word complex. It's really a complex system, but at the end of the day, we need to simulate it in order to be able to understand how the future climate will look like under different emission scenarios. So the main driver of climate change is GHG emissions, as I mentioned earlier, and a good example of greenhouse gas that we all know is the carbon dioxide, CO2. And we have also aerosols, but it's interesting to know that aerosols actually are working to make the climate colder, but they are out there. And when we try to decrease them because they are not healthy, they're actually contributing to the warming, but their role is not significant. So anyway, so in order to understand the future climate, anyway, we need first to understand how we're going to continue emitting those gases in the atmosphere. And that's a function of many other factors. For example, at the first place, we need to know how the population will grow in future, or how would be the GDP of different countries and in the global scale in future. How would we continue using generating energy and using oil, for example, and then how the technology would evolve in future, because that can have a strong impact on the emission of CO2 for energy generation, and so on and so forth. And then at the end of the day, after all these processes, we can estimate the concentration of those gases that we need to understand the future climate. So by just looking at that, we can say the prediction of future GHG emissions are so uncertain. And then that's why we use some scenarios or some stories to describe them, and we call them RCP emission scenarios. We have 4 different scenarios: RCP 2.6, 4.5, 6, and 8.5. RCP 2.6 is the most optimistic one, and 8.5 is called worst case scenario or no action scenario. According to the recent according to the latest publication of the IPCC, the Intergovernmental Panel on Climate Change, we are far from RCP 2.6. It means that we are almost lost that. It's gone. We cannot get there. So at least we need to deal with something about RCP 4.5. And I'm going to show how it's going to look like in future under that scenario. So, and then IPCC provides this information to all modeling centers, and the modeling centers, which actually responsible for producing the climatic models for future, they use this input to their models. So, and then if you look at the level of GHG emissions under those 4 different scenarios, we can see this figure here. The red one is the worst case scenario, as I mentioned, and then we have the most optimistic one as the blue one here. And these are the level of global warming that are expected under different scenarios. As you can see, under RCP 8.5, we are looking at 2.6 up to 4.8 degrees increase in the global average, uh, global warming average. And then this means a lot, actually. And then this is a great uncertainty that we need to deal with at the first place. And I'm going to show how it can impact the practice of engineering as well. So, and then after getting those emission scenarios, which are the input to the climate models, the climate model try to solve some equations, like some governing equations, to simulate those physical processes in the climate system, to project the future climatic conditions. So here is an example, schematic view of a climate model. So it tries to simulate the ocean, the atmosphere, and the land, and it tries to simulate different processes and the interactions between them through solving the equations. Here I'm showing the evolution of climate models. It started only with atmospheric models. So there was no ocean and land in the first generation of the models. Then ocean models emerged and then they coupled them to each other. And these days we are looking at very advanced models, which are called Earth system models. I can refer to, for example, the Canadian Earth system model, CAN ESM2, that is capable of generating future projections of climatic conditions under different emission scenarios. But this is how the climate model works. And by solving those different equations for different components and the interaction between them, it tries to simulate the future. But you can say it could be very uncertain because of some reasons that I'm going to show shortly. The first problem that we have with climate models is its multi-scale nature. So for example, in a climate system that I showed earlier, we can have larger scale phenomena, larger scale actually events such as planetary waves. They happen in larger scale. But at the same time, we have boundary layer impact, which is small scale. It happens, for example, very close to the surface of the ground, and then it's a small scale. But the problem we have with climate models is this resolution. So I showed you here the grids. These grids are so large. And because of that, they are not able to capture all those details and those processes. And then, for example, to give you an idea, we as engineers, we like to work with numbers. So here I'm providing some numbers. So the resolution of those grids for the regional climate models is something like 50 kilometers. So it means that each cell, each computational cell that we have in the model is 50 kilometer by 50 kilometer, roughly. And then the time step that we are looking at is 20 minutes. So it means that anything that happens in a scale smaller than 50 kilometer by 50 kilometer, or at the scale of the time lower than 20 minutes, we will miss that in a climate model. And looking at these complex systems that I mentioned earlier, we are only able to simulate this part in the climate model, and we are missing everything else. So what does it mean? It doesn't mean that that climate models are useless. That they are capable of generating a good projection, a good big picture of the future. But for engineers, it's not enough. As engineers, we need to work with accurate data, point data for that site that we are designing or actually maintaining or rehabilitating the infrastructure. And that's the gap that I mentioned earlier that needs to be addressed. So, and then on top of that, we have some other issues, and that's about those physical processes. Sometimes they are too complex, and the science is not there yet to describe those processes. And then sometimes they happen in the subgrid scales that I mentioned earlier. So the resolution of the model is not enough to capture those processes. I can show you some examples. For example, deep and shallow convection, they are part of the moist processes and they can contribute to rainfall and precipitation, for example. Another example is the cloud microphysics. So they can contribute to the cloud process. And then, for example, turbulent mixing and boundary layer and vertical diffusion. None of these can be simulated by a climate model, and they can impact the accuracy of the results that we are looking at from a climate model out. And instead of using actually or simulating the physical process, we try to use parameterization, which means that we try to approximate them. Very simple if I want to put it in simple words. So we try to approximate those processes and then we lose the accuracy. And because of that, the level of confidence that we can put on different climate variables that we obtain from climate models will vary. The highest confidence goes to temperature. Why? Because that has the most straightforward and simplest governing physical processes. So it's just a balance between the energy in the atmosphere and so on and so forth. After that is precipitation, because precipitation is a function of more other parameters, for example, cloud processes, moist processes, and so on and so forth. And the lowest confidence can be put on wind speed prediction of climate model, because as you can say, wind speed is a function of even more processes that cannot be captured by a climate model. And it's very important to have that in mind when we work with projected values that we get from climate models. So currently there are several modeling centers across the world, and they develop the global climate models. Different models that different modeling center develop may vary from each other in terms of their resolution. They may use different resolution for horizontal or vertical grids. The gridding method, the submodels or approximation methods that they use, the core numerical model that they use, and the details, the level of details that they use. For example, there are some climate models that they only use two types of land, for example, green or solid, for example, or there are some other models that they use four types of lands. You see, so that can make a difference in particular for wind processes, for surface, near surface processes, and so on and so forth. So that being said, now I'm going over the regional climate models. By regional climate models, we try to improve what I mentioned earlier. We try to increase the spatial detail that we get from a climate model. And then instead of looking at the global scale, we try to just focus on one area and develop a regional climate model for that area. Just to give you an idea of the difference, we are looking at the left, an output from global model, and the right is an output from regional model. So you can see the difference between the spatial detail and resolution that we get. And definitely as engineers, we can work with something like this at the right instead of the one at the left, because we are, as I mentioned, we're designing for a site, for a particular site, and we need to have the information for that location. So here I'm showing an example of the Cordex NA, which is the Cordex North American simulation domain, and this is a 50-kilometer resolution that covers the entire North America region. So, but again, to give you more tangible example, here I'm showing Ottawa. The red region here is Ottawa. Maybe I should have used Toronto, but anyway. So let's say you want to design anything for Ottawa, so then you need to have some information, and then it depends on which site you're looking at. And then here you can see different points, and you can imagine that you have the data on these points. For example, the green points are the results from a low resolution model. So we can see in Ottawa, you only have, for example, 2 stations. And then when we go to a better model with higher resolution, we are looking at these blue dots. So we have more information. And then if we make it even finer through some processes, then we are looking at these black symbols here. So we have that much information, which is more accurate and more detailed, I would say. So, and then in order, in general, all in all, at the end of the day, in order to use the climate data for a practical application, the first step is to put together the required raw data that we need to use. For example, if we are designing for a bridge or for a building, maybe we need to know about the July temperature or the extreme temperature, the minimum temperature, um, the maybe some wind speed information, and so on and so forth. So we need to extract those data from GCMs or RCP under different emission scenarios. And then we need to develop some statistical models in order to estimate the extreme values that we need to work with. And uncertainty analysis should be part of the picture and part of the game because, as I mentioned, the uncertainty is so high. And I'm going to mention how we can capture and address the uncertainty in our work. Um, then we also need to consider the impact of the climate non-stationarity on our design parameters. I'm going to touch a little bit on that in next in future slides. And then we need to consider also the impact of the design life or design service life of the infrastructure that we are designing. So the first challenge that I mentioned earlier is the uncertainty. The outcome that we get from different models will be different. For example, if you use two different models for the same location for the same time, you get two different results. So which one you should use then? And then if you use two different emission scenarios, you get two different results. Then there is a dilemma for engineers, and there is a big question. And there is another source of uncertainty as internal variability of the climate. But as engineers, we've been dealing with that part forever, so we know how to work with that and how to capture it. So, but in order to address the other two issues and the other two sources of uncertainty, we need to make an ensemble. So we need to use different climate models and we need to use different future emission scenarios to capture the range. So for example, if we want to have the temperature design for future, we don't rely on one model. We put some different models together from different emission scenarios and we get a range instead of one number. And that can provide some insights at least for design. For example, I'm showing an example of Ottawa again here. So this is the time variation of the projected changes in 1% January design temperature. As an engineer, this is actually a design parameter in the National Building Code. And let's say you want to design something, you want to design a building, you design it for next 50 years. So you need to know how the temperature, the extreme January temperature will look like in Ottawa in 50 years. So then you go through the steps that I mentioned earlier and you get something like that. And by looking at the black line, you see the average, and then the blue bars, they show the uncertainty. So for example, at year 2030, the design value could be something like between 2 degrees or 9 degrees, for example. So that's the range. We don't have a single value, but we get a range. And then we can do further analysis to actually identify the share of the uncertainty from different sources. For example, if the climate model is responsible for that uncertainty, or if the future emission scenario is responsible, or the interaction. And these types of analysis, they can provide good insights for decision makers in particular. So I'm not going to go to the details of that uncertainty analysis, but I just want to make it clear that we get a range instead of a single value. And that's a big challenge. That presents a challenge to engineers. So which value now they need to use? So there are some practical examples of addressing the uncertainty of the future climate. So this is an example I took from New York. Actually, I didn't have a citation to put at the time that I made this slide because actually this was on development at the time. But this is actually coming from the New York guideline for design under climate change. And here we are looking at the sea level rise under future conditions. If you look at the time, it's from 2020 to 2100. So we are looking at future. And this is for engineers to use an appropriate number from here for future design. And you can see they try to capture the uncertainty by using some percentiles. So the mean value here, for example, is the green line, but the 75, the 70, I mean the high estimate of the range is the 19th percentile of the range, and the lowest one is the 10th percentile of the range. And based on different factors, you can decide which value you need to use. There are some suggestions provided in that guideline. For example, if you are designing something very important, if this is very important for public, if you're building something like hundreds of millions of dollars, for example, uh, then it's a critical asset. Then really you need to design it for worst case scenario maybe. So then you need to go toward the upper level of this graph instead of using something from the lower end. So, and there were some suggestions provided, and that part is more, I would say, on decision makers and code developers rather than end users and like regular engineers. But they should be communicated to engineers through codes, guidelines, and the standards. But as you can say, it will be very hard to impose it in the code at the first place. So if you expect first to see them in guidelines and then to sign some kind of standards, and eventually they will find their way to codes. So, but this is how actually in practice, currently we try to deal with those uncertainties that I mentioned earlier. So the second challenge that we have with design parameters under climate change is the concept of the stationarity. To put it in simple words, I can say stationarity is the change with time. So when you have a design parameter, you expect it to remain the same throughout the life of the infrastructure. For example, you are designing a building for 50 years, and as engineers, we are used to working with a constant value for the design value. For example, you are designing for snow or for wind as two major important components of the design parameters for buildings in Canada. And then you're used to use a single value over the life of the building. But under climate change, that design parameters is expected to change through the time. And that can present another challenge to engineers because the distribution of the parameter will change with time. And then we cannot use the past practice. We cannot use the stationary assumption that is behind all the design guidelines and codes that we've been working with forever as engineers. And that concept should change in the future. There is a like expression saying that the stationary is dead. So we don't have a stationary anymore, and we have to go to a non-stationary code and a non-stationary design value. So the current design codes and guidelines, as I mentioned, they are all based on a stationary assumption, and they assume a single value over the life of the infrastructure, but that is expected to change under climate change. Again, I'm presenting an example here for Ottawa again. This is a design parameter that I'm showing. Let's say you're designing something for next 50 years. And then the infrastructure that you design, for example, a building is expected to work for 50 years. So then you need to design it for 2020 to 2070. But the design value is changing with time. So now which one you're going to use? Are you going to use the one at the beginning of the life or at the end of the life? So as you go toward the higher levels, the cost is increasing, and who is going to pay for that? And that's really a challenge because the owner really don't want to go there. They don't want to pay more. And then as engineers, again, we need to find kind of a trade-off between the cost and the safety and so on and so forth. For some infrastructure, it is more challenging, as I mentioned, in particular when it is dealing with the safety and health of the people and society. It's more challenging to decide because we try and we prefer to stay in the safe side because we are dealing with people's life and people's safety. For example, for bridges and for buildings, we really accept very low amount of risk, but for other types of infrastructure, maybe for roads or for some not important water network systems, then we can accept higher level of risk. So all in all, when we have a distribution or in a simple word, if we have a design value that changes with time, we are looking at a non-stationary design value. But if it is independent of time, it's stationary. But as I mentioned, stationary um, under climate change won't work anymore. So one way to capture that impact is to look at the trends. So definitely when there are different techniques, I'm not going to go through more details and make it too technical because it's going to be boring. But there are some techniques to detect those trends in time series, doing time series analysis and so on and so forth to capture the level of non-stationary. So another example I have here for non-stationarity is the annual probability of exceedance for a given return value. So we are looking at two different concepts that I mentioned earlier. So let's say you use a stationary design value. For example, you take it from the code without looking at climate change. And then you expect the probability of exceedance to be 2% over the life of the infrastructure. But what's going to happen after design under climate change? The probability of I won't say failure, but the probability of exceedance, instead of being 2%, it's going to go up to 35% at the end of the century. But if we use a non-stationary design value, which is definitely higher than this, and we have to pay more for the cost of the infrastructure, remains in an acceptable range. It never goes beyond 2%. But this one definitely is higher than the old one, but we make sure that we design properly and we take into account the impact of non-stationarity in our design. So one important thing in the non-stationarity concept is the design life. As I mentioned, the role of design life and commission year of the infrastructure will become more important in future when we go through the concept of non-stationarity, because it's all about the time, the change of the design parameter with time. And as I mentioned, for example, we design a road for how many years? 25, 30 years. That's okay. The design parameter may not change significantly over 30 years, so we can deal with that. But if you're designing a bridge for 75 years, then the change will be significant. So we really need to think about it and to find a way to address it. A good example of that could be a new Champlain Bridge in Montreal. That's a $4 billion, over $4 billion infrastructure. I think they designed it for 120 years or so, if I'm not mistaken. So then over that period, there is an expectation of a huge change for the design parameters. So I have some equations here, but I'm not gonna go over the details. There are two different ways to deal with to estimate the probability of failure under stationary and non-stationary condition. And you can see the difference in the graph. If we keep using non-stationary over different design life, you can see, for example, as the design life is increasing, the difference between the stationary and non-stationary design is increasing. So it means that for longer design life, we need to actually pay more attention to these concepts. So here I have just another example to show you some impacts of different parameters in the National Building Code. For example, we have some design parameters for temperature. We have January and July temperature as the extreme hot and extreme cold temperature. And here I'm comparing historical values from 3 different sources to future values. So these 3 guys, they are historical, and the other one, they are coming from climate change projection. And you can see that the changes could be significant, in particular for winter. For cold extreme, they are expected to change significantly in future under climate change. So here is just another example for the maximum mean daily temperature, which is one of the design parameters for bridges. And again, here we are looking at the historical and future changes. For example, in the figure at the right, the darker colors, they are showing the historical ones, and the green and yellow, they are showing the projection. And you can see everywhere the projection values are significantly higher than historical ones. So I just have some more examples here for different climatic parameters. These are again July and January design temperatures relative to historical baseline period. As you can see, everything is increasing in summer and actually warming in winter. As you can see, the temperature is expected to decrease, for example, by 80%. So another example for the total precipitation. The total precipitation is expected to increase everywhere across the nation. However, the seasonal and temporal variation of the total precipitation might be different. And again, here is an example of Ottawa. It is expected to have higher annual total precipitation at the end of the century by 30% compared to historical baseline period. So, and then here I'm just talking a little bit about more advanced design values such as ice accretion. Ice accretion is a challenging parameter because there are many contributing factors. For example, the type of the precipitation should be freezing rain, the temperature profile is important, and the wind speed is important. And because it's a combination of several different parameters, the uncertainty of the projection for such parameters will be even higher. And this is something we really need to pay attention to in our design. So here I'm having an example of my work on prediction of the temperature profile and the ice freezing and ice accretion event that was perfectly captured for this event on January 5th in 1998. Maybe you remember that event, or maybe you've heard about that catastrophic event in January 5th, 1998 in Montreal. So the other parameter which is highly uncertain is wind. As I mentioned, wind pressure is very important for design of many buildings and bridges. So here we are looking at the potential changes at the end of the century under the worst case scenario. We have two different return periods of the wind, the 100-year and the 50-year, the 10-year and 50-year ones. For wind speed, although it's highly uncertain, the changes remain small, and that's maybe a good thing about the wind speed that we can mention here. And we are looking at the changes. You can see the percentage change in the wind speed in different locations across the nation will remain limited to something like 15%, I would say. And in some locations, it is expected to have decreasing wind speed, as you can see here. So just some more a statistical analysis here. I'm not going to go over the details, but here I just wanted to present an example of how we can capture the impact of non-stationarity in our statistical analysis. And these type of analysis are needed to inform guidelines and codes and standards. So here I'm showing an example of the wind speed and how it is expected to change under different climatic conditions and how we can capture that change in our codes and guidelines. So with that, I'm just going towards some summary and conclusions. So maybe I can just present one slide on the NRC's Climate Resilient Buildings and Core Public Infrastructure Initiative, which was conducted within the past 5 years. Actually, at NRC, the initiative was led to develop some decision support tools, including codes, guidelines, and models for the design of resilient new buildings and core public infrastructure, and for the rehabilitation of the existing ones. And in this way, we can ensure that the impact of climate change is captured, and the future CPI that includes bridges, roads, transit, drinking water, and so on and so forth can be designed in a resilient, climate resilient way. So we got funding for that project from Infrastructure Canada. And then it was in support of the Pan-Canadian frameworks on clean growth and climate change, and in support of the green infrastructure objectives of the Canadian government. So you can consult with those links, and you can find the report in addition. That's a very interesting report if you're interested. So in summary, I discussed today that the average warming across the nation is twice of that global scale, even with greater warming in the north. Extreme hot, cold, and extreme cold temperatures. They are expected to be warmer in the future, in particular in locations in the north and in BC. Extreme rainfalls are projected to increase everywhere across the nation based on the temperature scaling method that was used in these projects. And you can see it's expected to have something between 20 to 30% in most of the locations. The snow loads are challenging ones because the snow loads, due to the warming, they are expected to go down. However, for example, if you want to design something with lower load in future, it's going to be challenging because the decision may result in some uncertain situation that may impose higher risk for our infrastructure. Given that the magnitude of those projections, in particular in mountainous area, is highly uncertain. So ice accretion, as I mentioned, is expected to decrease in other areas, but in north, it is expected to increase up in higher latitudes. The wind speed, the change will remain not significant, will remain relatively small for most of the location, between 6% increase up to 15% decrease in some locations. The selection of RCP emission scenario, as I mentioned, that's more on a higher level of committees and decision makers, and that's a delicate decision to make. For example, Bridge Code adopted RCP 6 for the future cycle, and it depends on many factors such as time horizon and so on and so forth. And then a special attention should be given to the uncertainties, as I mentioned, and the time variation of climatic design data needs to be taken into consideration, in particular for long life infrastructure. And with that, I can finish my presentation. Here I'm showing a photo from Edmonton. Actually, I was there at the day, and that you're looking at a blanket due to a wildfire back in 2019. That may be a midday photo, like at the middle of the day, but that's the blanket from the smoke of the wildfire back in 2019 in Edmonton. Okay, thank you very much for the attention, and I'll be happy to answer any question.
Thank you so much, Dr. Shirkhani. It was very interesting and informative presentation. Yeah, I really enjoyed your scientific approach to the future of climate and for uncertainty and for driven altogether was fantastic. So let's see any of our value audience have a question. Dear friends, any questions so far?
I might have a question.
Yeah, sure, go ahead.
Right. My name is Mohammad Mashrouf. My professional is Sean Mashrouf. We are doing site service and stormwater management. I really enjoyed. Congratulations on your wonderful presentation. I have what I understood from this is there's average, the stationary, non-stationary. Stationary is following codes and standards, textbook, what's that? And non-stationary is this new, utilizing this new first-hand scientific estimation of this stuff, these terms. This is one thing. Specifically, now I want to point out one specific way of design. When we are doing stormwater management or sewer design for storms, we are for estimation of the how much storm or flow rate we consider for our design. We use hydrographs. Hydrographs are coming from statistics and each municipality, they had their own hydrographs, which utilizing those hydrographs, we determine the flow rates, and the same standard from the same standard, municipality dictates what storm event is being used for what type of infrastructure. Example of that is City of Toronto, downtown Toronto. It's to design public storm sewer system. We have to use 2-year storm for the design of the storm. Now the question is this: I'm as an engineer sitting behind my desk, and I'm doing this. I'm doing of course, the date on the standard of City of Toronto is 2006. I tell you how old is that. And if I say this is non-stationary approach, and the global changing hasn't been considered in this design, so I put together my design and the report and the drawing and stuff, and send it to the city. Right away, the city engineer is gonna commented, "Oh, this is over design," and and the engineer should redo the design because it's against the standard. From other side, if nobody catch me and the design is approached, for some reason, it happened before in all past projects, the client, especially in major projects, their clients review that by third-party consultants. Bottom line is this: we have to be very, very careful on or whatever we provide as engineering service, and when we seal it, stamp it, you have to be careful. It's not over designed, it's not under designed, and it's kind of about to be perfect. Otherwise, we have problem with liability. My question is this: how we can take these steps toward this? I appreciate this. I cannot understand how in or my line of expertise can apply this brand new science. Sorry.
Yeah, thank you. Thank you for the question. Yeah, I totally understand the concern that you raised here. Yeah, it's good example that you mentioned. It's maybe worth of mentioning that my areas of expertise in water resources engineering as well. I did my PhD in that area, and I'm working on stormwater, different stormwater areas as well. So I totally understand the concept of 2-year like hydrograph and using two-year design storm and so on and so forth. But yeah, at the like you and the other engineering practitioners, for example, you're the end user of those codes and guidelines and standards, as I mentioned earlier. And this is really up to the municipality levels first, and then provincial and federal government, and so on and so forth, up to the higher levels, to prepare those for end users, for engineering practitioners. But I think for engineering practitioners, it's also important to educate themselves about those topics and those ideas, and to have the knowledge to be ready to implement those in future. Because one challenge that actually we have in codes which are enforceable is to make them simple to use. Otherwise, it could be very misleading, and it may result in human mistakes like engineering mistakes and things like that. And that's really a big challenge for developing the codes. And the main idea of a code is to be simple, for example. But as I mentioned earlier, like we are a little bit behind on that. And Canada is one of the pioneer countries anyway on that aspect of the engineering. Canada is if it's not the first, I think it's the first. It's the first country that tries to incorporate the impact of climate change in the code, in the national building and national bridge code, for example. Um, and we are ahead of many other countries already. But there is the gap, and I mentioned that earlier. Yeah, I do agree with you that this gap currently exists, but things are evolving and improving. For example, under the initiative that I mentioned at NRC, within past 5 years, we developed a lot of guidelines and a lot of tools and standards. For example, I was part of the 3 different committees. One example that I can give you is a technical guide of the Canadian Standard Association for the use of IDF curves. You might be familiar with that one. And then we updated that for climate change impact. So now, if you look at the newest version, then it has some updates on climate change, how it can be incorporated in the IDF curves, for example, which is actually the design value that you need to use in the design. I mean, yeah, these are some examples, but I do agree with you that there is currently a gap that should be addressed. But things are evolving, and I'm thinking that in future, like in 5-10 years, most of the guidelines and the standards will include provisions and sections on climate change. And but it takes time. It takes time to get there for sure.
If I may, I want to weigh in here. And the thing is that up until now, we as engineers could shelter behind the codes and uh, national standards. For example, in the building code, there are few schedules and few charts and defining, for example, the wind speed, the snowfall, the maximum rainfall, expected temperature differences, etc. But the important thing is that in the recent years, courts do not agree that engineers are bound to the code. Courts expect from engineers and professionals more than that. And while we are waiting for the Canadian standards and National Research Council to weigh in and give us up-to-date information and codes that we can use. But at the same time, I want to emphasize, especially for my colleagues who are professional engineers and are working in real projects, it is important to make your company and yourself safe against any lawsuits in the future, because the courts are changing their the type of reaction that they are dealing with engineers right now. The bottom line is that, for example, last year there was a huge storm in Barrie, and a couple of residential buildings lost their roofs. The roofs were tore down and the buildings were damaged. And especially because of one of those buildings that was a daycare. And the lady who was in charge of the daycare, as soon as she heard the sound of the wind and the building squeezing and screeching, and so she brought every child to the basement, and that saved their lives, because the roof of the same building was torn off and half of the building was destroyed, and children were safe because they were sheltered in the basement. And because of that accident, there was a lot of news coverage. It was all over the news outlets, the TV news outlets, and newspapers everywhere. So the bottom line is that if an engineer designs a new roof for that area, and does not go above and beyond the building code, he cannot defend himself in the court, because the judge will say, where were you when that happened? Everybody knows about that incident. You cannot hide behind the code that was uh, prescribed like 10 years ago or 20 years ago. We are using the building code that was basically enforced in 2012. So this is just a reminder to my colleagues. Please collect any information that you can from the websites that Dr. Shirkhani showed us at the end of the presentation, or any other sources. And please write it clearly to the owner, to the client, if it's the municipality or anybody else, and describe to them the challenge of the changing climate, and let them take the responsibility. If they insist that you have to go with the previous practice, they have to take the responsibility, because otherwise you would be liable, and courts are not very friendly with this situation. I had to reiterate this item. Yeah.
Thank you, Mr. Khulabale. That's a very good point. Yeah, it's very important to know that. Yeah, thank you for sharing. Yeah, I think it's very, very informative for me at least. Thank you.
No problem.
Okay, so we have comments, have a question. Yeah, please comments, please go ahead. Please unmute first. Sorry, please unmute.
Can you hear me?
Yes.
I didn't already. Okay. Thank you very much for the perfect presentation.
Thank you.
There is a famous word. It says that the climate crisis will not wait for us. But, and thanks to all different voices claiming this and that is here in the newspapers, television, everything, all the kinds of the media. Mostly they are talking about the including, they're saying, they are saying about the fossil fuel interest, and deniers are spreading all kinds of myths. In general, what is your opinion about this? What's happening or what we can do?
Okay, you are referring to fossil fuel use in particular?
Yes.
Yeah, that's a very good point. Thanks for bringing that up. Yeah. First, you mentioned that climate crisis won't wait for us, and I can just complete that with saying that engineers can't also wait for climate science. So they need to do their design as well. So that's another thing to complete that. Yeah. And in terms of fossil fuel, yeah, I think for Canada, as an example, you know that there are good plans in place. Some provinces already phased out the use of fossil fuels for generation of electricity, for example, and they are totally phased out now in some provinces. And there are some plans to go toward more green and blue ways of generating electricity in many provinces already. And some other provinces and territories committed to certain time to phase out the use of fossil fuel for generation of electricity, as an example. And other things that I can mention is the future of transportation will be a very important sector, because transportation is one of the major contributors to the use of fossil fuels. And as you can see these days, there are many electrical cars around, and also many governments, not only in Canada, but across the world, they support the electric cars by some incentives and so on and so forth. So that can be a play changer, I would say. And another sector that I believe may change in future is the future of the material. For example, cement and steel, they are two major materials for civil engineering and for infrastructure. And then those are also responsible for a good chunk of the share to the generation of the GHG and to the emission of the GHG gases. And I see that that is also changing kind of with introduction of new materials and recycling of previous material, used materials, use of the actually the construction waste in other sectors. For example, now the concrete waste, they are being used sometimes in asphalt aggregates and as the base of the pavements. There are different initiatives and technologies developing, and I think in future, in that sense, we can improve definitely. And if we look at the recent emission scenarios that was published by IPCC, the Intergovernmental Panel on Climate Change, we can see that RCP 8.5 is marked as kind of an outlier. It's very hard to get there. That's not going to happen because that's kind of totally no policy and like using fossil fuel up to end of the century. And this is something at least at this stage we expect not to happen in future.
Thank you very much.
Absolutely.
Okay, Mr. Mirpurian, please unmute. Yeah, thank you.
Thank you for the information. Just for clarification, Mr. Khoda Bande, yeah, that's his name, stated that you have to go beyond the code. That's not right. In the court of law, the code is the Bible. You follow the code, you are covered. If you want to do beyond that one, you have to go and face the lawsuit by the owner why you did do more than was enough. That happened. So the code is the Bible, follow the code. That was his statement. This is very right, but don't go beyond that one. You satisfy the code, you are okay. You don't do that, you either this side or that side will sue you. Thanks. No further statement.
Okay, thank you so much. So for your comment, Mr. Mirpurian, Mr. Hamidi, do you have a question or comment?
Yes, actually, I have a question, if you don't mind. Just you mentioned about the sea level. I'm more concerned about the coastal big cities in Canada, east and west. So we assuming if this global warming might be happen in future, maybe worse what we hearing these days. And then, so if that sea level really rise, what Canada, how they are prepared for that, especially the research center like you in Ottawa, or all those universities on the coastal big cities, what they doing as far as the research for the new design for the building, or new design for the roads, or any changes of the code for those kind of design. That is my question for, let's say, for the future. Yes.
Yeah,
Thank
thank
you.
you very much. Thank you very much. That's a very good point that you mentioned. So actually, under the initiative that I mentioned earlier at NRC, the coastal hazard emerged as one of the most important ones. And actually, an emphasis was put on the coastal hazard. And actually, we developed a coastal flood risk assessment guidelines, a CFRA. So if you Google it, if you look it up, you will find it. It is called Coastal Flood Risk Assessment Guidelines, and this is something was developed under that initiative. And then what we are looking at coastal areas currently is the hazard. As you may know, like there are different steps. First, we have the hazard, then we need to define the probability of failure, then the risk, and then the resilience eventually. And then at the first step in this guideline, the coastal hazard was explained perfectly, and then different types of coastal hazards identified and explained, and what would be the potential changes that may happen into the coastal hazards. And on top of that, different adaptation methods proposed in that document. So yeah, that's an important point. And there are actually different barriers to adaptation as well, but those could be also addressed by appropriate approaches and so on and so forth. But at the end of the day, yeah, I do agree. Coastal hazards are important. Um, we try to identify the hazard at the first place, and then to propose some mitigation and adaptation measures. Maybe a good example of that adaptation is nature-based solutions that are very popular, and they will become popular in future as well. You can think of, for example, planting in the coastal areas, and they can damp the storm surge and the waves to a very good level. And by that nature-based solution, without adding any like unnatural component to the coastal area, we can protect many of our infrastructures against the wave runoff and things like that. Yeah, that's just one example came to my mind.
Thank you.
Absolutely.
Okay, thank you so much. May I have a question, but not very scientific, maybe? So, in the first of your presentation, you showed us the Canada's target for 2030, and by the most optimistic scenario, the target won't be, fulfilled. Just I want to know what's the criteria to set that kind of target, and what will happen when we know the target will not be fulfilled.
That's a good point. Yeah, actually, I think you're referring to the RCP emission scenario 2.6, the most optimistic emission scenario. Yeah, actually, these scenarios designed, I think, at least 6-7 years ago, roughly. And then at the time, the most optimistic one was based on the Paris Agreement. If you know that agreement, I think that's a famous one. So that was based on the Paris Agreement, and at the time, all the countries promised to do their shares and to they committed to take some actions. But with policy and political things that may evolve and may change with time, they didn't happen. And then that's why currently they are not saying that for sure we won't get there. They are saying it's very difficult to get there, and that's why I call it the most optimistic one right now. And even in the latest report from the U.S. Report on climate change, which was published late 2019, if I'm not mistaken, they used RCP 4.5 as low emission scenario for many examples and for in many cases. Actually, they kind of accepted that 2.6 is also very far from us now, currently, based on the recent things that we've done and we've been doing since then. It's going to be more challenging and more difficult to achieve that goal.
Yeah, okay. Thank you so much.
Thank you for the question.
So, if there is no question remains, any question? Yes, Mr. Afshari, please unmute.
5 seconds question, please.
Okay.
Mr. Shirkhani, yes?
Yes, yeah. Yes, sir.
What is the picture behind you? What is that one? That picture?
Oh, the picture. That's the University of Ottawa campus, one of the buildings at the U Ottawa.
Oh, okay. That's nice. Bravo.
Yeah, I was there in Gatineau Park last week. Oh, fantastic.
Yes, yeah. At this time
Fall
of the
is
year, yeah.
beautiful. It's like a golden cover everywhere.
Yes. You see a full spectrum of colors in Gatineau.
Yeah, and it is so sad. For example, maybe next generation cannot see it like in nature.
we should try. Yeah.
Yeah, we should do. Yeah, we have to do our best. Yeah, Mr. Ross, do you have a question?
Oh, just one very quick question.
Yeah, sure.
Okay, we heard of the detrimental effect of sea level rise. Is there any benefit of sea level rising in terms of structure or any other aspects?
That's a good and challenging question. I think in terms of like civil engineering infrastructure, I personally can't speak to that. Like, what type, any type of infrastructure that I can think of will be vulnerable to sea level rise, I would say. But maybe there are some like environmental benefits from having higher sea level rise in some areas. Maybe I'm not too sure. Yeah.
Okay. The reason I asked was I remember when I was in university back in U of A, Alberta, we were kind of discussing about Turkey. In Turkey, I believe, was it Black Sea or something, the sea level was lowering, and that was damaging a lot of bridges because of kind of gouging effect. The foundation of bridge was exposed and a lot of bridge failure and things like that. So that's what I heard back then. Sea level falling is really bad for infrastructure. But no one's talking about any benefit of sea level rising.
Yeah, that's something. Yeah, because sometimes there are some benefits that one can think of. For example, in terms of warming, maybe there are some good benefits for agriculture section, for example, maybe, and for sea level rise, I'm not too sure, but I can think of maybe some environmental aspects for ecosystem, for fish habitat or aquatic life. Maybe there are something there, but I'm not aware of that. Yeah, I can't speak.
Thank you.
Thank you.
Yeah, hopefully Toronto will be Miami of North. Yeah, Mr. Hamidi, please go.
Yes, actually, I heard. I'm not sure if it is true. The Japan, they are working on the project that to making a city above the ocean, above the water, let's say, or sea, and then that is related to this global warming. They might, if this happened, that the Japan will be in trouble for sure,
Yes.
all over the island. So I heard just they working on the city above the sea. Have you heard about this project or anything related to that?
No, unfortunately, no, I haven't heard about that types of project in Japan. Yeah, but that
Okay.
sounds ambitious and like interesting.
Okay then. So I
thanks,
was
thanks
just
for sharing. I can look it up and learn it. Yeah.
right. Anyhow, anybody else might heard about this?
No, I heard something living under ocean.
Under ocean. Okay.
Yes.
No, I'm talking about above ocean. Okay. So just to making the city above and then with all facility, just like a city.
Yeah.
Yeah.
Okay.
Yeah, eventually, we may migrate to Mars maybe at some point.
Yeah. Okay. Okay. Thank you so much. Looks like there is no more question. And thank you so much, Dr. Shirkhani. It was
Thank
a
you.
great pleasure having you and knowing what you are doing there. Hopefully, I don't know how much politics affects your effort, but hopefully, our politicians listen to scientists.
Yeah, that's a gap that should be bridged. Yeah.
Yeah.
Yeah, thanks for having me. Yeah, it was really pleasure to meeting you, everyone, and to to talk to you. It was very interesting, and I really enjoyed. Thanks.
Thank you. Thank you, everybody.
Okay.
Thank you.
Have a good rest of your night. Bye.
Nice to
Thank
see
you.
you.
Bye.
Take care. Take care.
Take care, everybody.
Thank you.
Okay.
See you
Bye.
next time.
Thank you. So,
Bye there.
thank you.